Hey guys, welcome to Chapter 8, Lesson 1. We're going to start on Chapter 8, Earth Systems. The reading assignment today is on our first sticky note. It's page 207 here on the opening story about hybrid electric vehicles. And then we're going to end on page 221 at the checkpoint questions. Our study tip today is going to be to transcribe your sticky notes into concept maps to help your brain organize information. I'll do some for you today, and then in the future I'll give you skeletons to fill in yourself. Okay, so I'll give you like ideas for concept maps, and then your job will be to fill them in. Obviously, all of this is going to be optional. It's just a matter of what you feel is going to help you study the best. Our first sticky note today is a case study of hybrid electric vehicles, and it's kind of going to be examining the differences between HEVs, which are hybrid electric vehicles, or IC engines, which are internal combustion engines. Some positives about hybrid electric vehicles is that they use little to no gasoline, and so that's usually people's drive when they're going to purchase it, is because they don't want to pay for gas, or they don't want to pay for as much gas, whereas gasoline is used for internal combustion engines, and that comes from fossil fuels. Now, what a lot of people don't know is that you have to mine in order to get fossil fuels, but you also have to mine in order to get the scarce metals that you use to make things like lithium batteries, which is what hybrids run off of. Now, there's a couple consequences of mining that are kind of universal. It doesn't matter if you are mining fossil fuels or you're mining lithium. The first one is, of course, habitat disturbance, which reduces biodiversity, gets rid of habitats for species, and kind of fragments everything. Erosion is the movement of sediment and things that isn't really supposed to happen. You can't have very good soil if you're having erosion constantly. And water contamination, and we'll talk about that a little bit more later on in this chapter. Now, a common misconception that we need to clear up right away is that all electric vehicles are not the answer to our growing transportation needs. Okay, hybrids and things like that are not without their environmental impacts. For example, battery manufacturing for these hybrids uses non-renewable metals, and metal mining creates acid mine drainage and fragments habitat. So this is not, the magic cure to all of our fossil fuel problems. Next, we have how did Earth form? And this figure here is really fantastic about how the solar system and Earth formed. It says that the processes that formed Earth 4.6 billion years ago determine the distribution and abundance of elements and minerals today. Okay, so first we have this kind of cosmic cloud called a nebula. It spontaneously condensed. The center is, of course, where most of the mass is in the gravity, and so that created the sun. The planets began to orbit around it. Eventually, they were made into single bodies, as well as the asteroid belt. Earth is here. Here's our solar system. To Earth's formation was 4.6 billion years ago. Hot molten sphere, so it was basically made of lava, and it was bombarded with debris from the sun and other planets and asteroids. Heavy metals like iron sank to the core, and light elements like silicon floated at the surface or the crust. Gases that were released during this time formed the atmosphere. And an important thing to note is that the number of elements back then is the same as the number of elements now. So we have the same amount of iron, we have the same amount of oxygen, we have the same amount of water as we did back when the Earth was formed. Now, these elements and things like that are not evenly distributed across the globe. So elements are distributed unevenly across the globe. Some of them are readily available or abundant, like silicon dioxide, which is the main component in glass and sand. Others are more rare, like diamonds, which are based in carbon. And the more rare, more valuable elements and minerals have kind of driven many conflicts. If you've ever seen the movie Blood Diamond, it kind of gives you an idea of the conflict that's going over these precious metals. There are a finite supply of mineral resources, and yes, that includes natural diamonds. We've been able to create diamonds in a lab, and that's what my engagement ring is and wedding ring. It has a bunch of science diamonds, as I like to call them. They're diamonds made in a lab. Now, as we get down and we're having to dig more and more and more to get to these precious metals, we're actually having to use more energy to dig deeper, which costs money for the miner, and whatever cost of the miner then extends to the consumer. So the more expensive it is to mine something, the more expensive it is to buy it. Now, Earth's layers are broken up, and you've probably heard of like core, mantle, crust in the past, but we're going to be a little bit more specific here. So we have the solid inner core, which is nickel and iron. We have the liquid outer core, which is nickel and iron. The mantle includes the asthenosphere, which you guys talked about when you did your graham cracker lab. And so the mantle is all three, 1, 2, 3 layers. Magma is what's in the mantle, and it's molten rock, so melted rock. The asthenosphere is kind of plastic or ductile, so it's kind of like frosting, where it's not a liquid, but it's not really a solid. Then we have the solid upper mantle and the crust. These two layers form the lithosphere. The lithosphere is made up of plates. Lithos means rock, so these plates, and they move through convection currents, which we call plate tectonics. Now what I've done is I've kind of made some notes on this figure to kind of help my brain remember things. I have the core, the solid inner core, liquid outer core, nickel and iron. I have the mantle, which is made of molten rock or magma, circulates in convection currents. I have the asthenosphere, which is the outer part of the mantle, and it's semi-molten rock, so semi-liquid. And then I have the lithosphere, which is the outermost layer of Earth, including the mantle and crust. So this is kind of just another way for me to organize the same information, only using a figure from the book instead of drawing my own. All right, next we have convection currents and the theory of plate tectonics. So, like I said before, convection currents drive plate tectonics. Radioactive decay in Earth's core creates heat. That heat from the core heats up the magma, and it rises because it's less dense. Then when it gets to the surface, it's obviously cooler than the core, and cooler magma sinks because it's more dense. Now, every now and then, magma will kind of like make its own way over here, kind of coming up to the surface on its own if it's extra hot and it needs to release some of that energy, and that's called a mantle plume. And sometimes these mantle plumes create hot spots. We'll come back to this later, but a lot of times when you see like a volcano all by its lonesome, it's because of hot spots. All right. Now the theory of plate tectonics comes from a gentleman named Alfred Wegener in the early 1900s, and he says that the Earth's lithosphere is divided into plates, most of which are in constant motion. He's actually the same guy who proposed Pangea, and he used rock formations and fossils as evidence. Okay, now if we look down here at the figure, we can see that these rocks are kind of moving or kind of distributed along these continental lines, and these aren't together anymore, so the only logical explanation is that they were once in this order. Another thing, the fossil evidence is that this is a freshwater reptile, and they found fossils of it on both South America and Africa, and so since we know it's freshwater, not a saltwater creature, we know that they would have to been right next to each other in order for this to be plausible. So the tectonic cycle is the sum of the processes that build up and break down the lithosphere, and we're going to talk about that right now. But first, another common misconception. Okay, a lot of people think that now plates have stopped moving, and that's absolutely not true. Plate motion has not stopped in present times. Earth's geologic systems are dynamic. Plates are shifting. Islands are forming even now. And a couple of evidence of that is the Haiti earthquake a couple years ago and the Mount St. Helens eruption in the 80s are both evidence that plates are still moving. All right, now next is the differences between the tectonic plates. We have oceanic and continental. Oceanic plates are very dense. They're rich in iron, and they actually sink below continental plates whenever they meet each other. Continental plates are less dense. They're made of silicon dioxide and they float on top of oceanic plates. Okay, kind of the same way that ice floats on water. When plates move apart, new lithosphere is made. So new rock is made, new crust is made, and when plates move together, lithosphere is destroyed, and that's called subduction. We'll talk about it in just a second. A couple more notes that I made on this figure that I think will be fabulous to kind of help us understand what's going on here is everything that's happening at these different plate boundaries. So first, the blue highlighted ones, or the collision zone here, we have the formation of mountain ranges, which happens at convergent boundaries, continental to continental convergent boundaries. An example is the Himalayas, which is in between India and China. Next, we have increased seismic activity at transform faults. An example would be the west coast of the USA and California. We also have the formation of oceanic crust, which is the spreading zone, which all the spreading zones in here are red. And the largest example is the Mid-Atlantic Ridge. It's the spreading zone that goes through the whole ocean. And then lastly, we have volcanic activity, which happens in subduction zones, which are the blue areas. And an example is the Andes Mountains in South America. All right, now there are a couple of very drastic effects of plate motion that kind of helps us understand what's going on in the world. First of them is evolution. We have measured this throughout the entirety of geologic time. We know that when the continents shift, climate changes, geographic barriers like mountains, valleys, rivers are created or destroyed whenever continents shift, and allopatric speciation occurs, which create new species. Now, if you can't remember how allopatric speciation occurs, I would suggest going back to chapter 5 and reviewing that. Another effect is volcanoes, which move over hotspots and also happen in convergent zones. They spew ash, gases, and lava. Plate motion leads to an extinct volcano trail like Hawaii. And if we move over here, we can see that. It says a plume of magma or column of lava lies in a fixed position as the Pacific plate moves over the plume of volcano forms, creating a steady succession of volcanic islands. So we know that if this is the hot spot, the island of Niihau was formed 4.89 million years ago when that region of the Pacific plate was over the hot spot. So this point, this island used to be right here. But now over time, it's moved in this direction, and that's how we can kind of track the succession, if you will, of volcanic islands, which is kind of cool. All right, so next we have our convergent and divergent boundaries. First we have divergent, and I've kind of drawn the direction of the convection currents that help to push these plates apart. So plates are moving away from each other. It forms new crust. It brings copper, lead, and silver to the surface from the mantle. A big example of this is seafloor spreading, which happens when there's divergence in oceans. And so whenever there's a divergent boundary in an ocean, we call it seafloor spreading, because it's basically making the seafloor larger. Fun fact, the Atlantic Ocean is actually getting bigger due to divergent boundaries, and the Pacific Ocean is getting smaller thanks to convergent boundaries. And so when convergent boundaries are coming together, one plate is subducted under the other one. Plates move towards one another. It actually destroys crust, so this crust is actually destroyed because it's getting liquefied back down in the mantle. Usually the more dense plate subducts, and as we know from before, oceanic plates are much more dense than continental plates, so they're going to be more likely to subduct. Now there's one exception to this, and it's continental-continental convergence. Because continental plates are so not dense, since they both have low density, they end up floating on top of the mantle. So the mantle and the asthenosphere is still subducting, but the crust itself is staying up. The crust forms mountains, and you guys saw that when you did your graham cracker lab. And our last kind is going to be our transform boundary, and this is when plates move sideways past each other, and a lot of times they're associated with fault zones and earthquakes. And this is the San Andreas Fault in this picture, and so it's really, really jagged, associated with earthquakes. And so another idea for a concept map that I did was the zones of plate contact. I have divergent, convergent, and transform boundaries, and then I gave a little fun facts about each one. And another one that I did, because convergent boundaries can sometimes be confusing as to what they're actually creating, I created this one, and it talks about the different types of convergent boundaries and as well as the outcome. So what happens after these boundaries are created or in motion. Okay, so I have continental, oceanic, 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 continental, continental. And here's what happens. All right, next we have faults and earthquakes, because we're talking about transform boundaries. Okay, so a fault is a fracture in rock where there's movement, and so these are associated most often with transform boundaries. The fault zone is where movement has occurred already, so these areas are really jagged. The pressure then builds up and there is an earthquake. Okay, and so you can kind of simulate that with your hands. If you push your hands together really, really tightly, like you're squeezing your hands together, and then all of a sudden you're going to try to move one of them, and then it breaks. Okay, and then you have your hands like this. That's kind of what happens when there's an earthquake. Okay, so the pressure builds up, pressure, 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 pressure released, and that's when an earthquake happens. And then the earthquake is defined as when rocks rupture suddenly. Okay. Now, seismic activity is how we measure the frequency and intensity of earthquakes. Usually this happens along fault zones. The San Andreas Fault in California is one of the largest monitored areas in the world. What happens is the earthquake actually happens underground. The epicenter, or where we measure the earthquake, is at the surface, and we measure it through the Richter scale, which measures the earthquake magnitude. Now, it's a logarithmic scale, kind of like pH is a logarithmic scale, which means that the value or the magnitude increases by 10 by an increase in 1 unit. So the difference between 4 magnitude and 5 magnitude is actually 10, not 1. Okay, similar to pH. All right, let's talk about what these kind of things, these natural disasters kind of do to humans. So we have humans and earthquakes. Small earthquakes happen daily. We don't feel very many of them. Moderate to large earthquakes end up in collapsed structures, fires, death, contaminated water, all sorts of horrible things. Increased earthquake magnitude means there's going to be an increase in damage, especially if it's a highly populated area. Anytime that we build buildings on fault zones, they're actually designed to withstand motion, and there are special things that those engineers do in order to make sure that if an earthquake happens, their beautiful building isn't going to come crashing down. Humans and volcanoes. 85% of volcanoes are on plate boundaries, others are on hot spots. They put cinders, ash, dust, rock, and lava into the air and down the side of the mountain, and so it causes habitat destruction and alteration. It lowers air quality, and not just in the immediate area either. All of these things are spread around the globe by air current, so the air quality can be lowered all around the world, not just in that one area. So I wanted to point out this figure real quick, because it shows you the difference in the locations of hot spots. So hot spots are in the middle of plates. Okay, subduction zones that have these volcanoes are all around here, and so the reason that they call this purple area the Ring of Fire is because it has a very high concentration of volcanoes. But what you should also notice is that along with these volcanoes, we have a subduction zone. So like almost every single volcano is either associated with a subduction zone or a hot spot. Okay. Next, we're going to talk about the rock cycle, which is the constant formation and destruction of rock, okay, which is the slowest of all cycles, slower than the plate tectonics, slower than carbon cycles, slowest than every cycle. And now a rock is defined as one or more minerals, which a mineral is a solid chemical substance with uniform structures. And so it can be either a structure with a compound, like we'll see down here, or a single element like gold. Like if you buy a gold bar, that's a single element mineral, only has gold in it. But like this one is pyrite, which is iron sulfide, and that's going to be a compound. Graphite is a single element because it's just carbon. That's what you find in your pencils. And then table salt or halite is sodium chloride, and that's another compound. Okay. All right, next we have igneous and sedimentary rocks. Igneous rocks form directly from magma. We have two kinds. We have basaltic and we have granitic. Basaltic is mostly found in oceanic crust. Granitic is mostly found in continental crust. Basaltic have more heavier elements like iron, magnesium, calcium. Granitic have lighter elements like silicon, aluminum, potassium, and calcium. Then we also have another two types of igneous rock based on where they formed. Intrusive cools underground. Extrusive cools above Earth's surface. Intrusive we end up getting to them through fractures, which are cracks as the rocks cool. And these form these things called veins, which are concentrated deposits. And those are the places where we really want to mine, because there's going to be concentrated deposits of profitable ores like silver or gold. Extrusive mostly get to our surface through volcanoes, seafloor spreading. They cool pretty quickly. It's way colder at the bottom of the sea than it is in the mantle, so it's going to harden, cool really, really quickly. Sedimentary rocks are sediments compressed by overlying sediments, so kind of layers and layers and layers and layers compressed over time, made of mud, sand, and gravel. Usually we see these in areas that have sand dunes, mud flats, and lake beds. They can either have uniform composition, like sandstone and mudstone are kind of the same elements over and over and over again, versus heterogeneous, which is a mixture of things like cobbles, gravel, and sand, and they're not very uniform at all. Sedimentary rock is where we keep our fossil record. Well, we didn't keep it, it just happened over millions of years. But sedimentary rocks is where we can find fossils and we can easily extract them. All right, there's obviously not going to be any fossils in magma. All right, now last type is metamorphic rock, and it's when other rocks undergo increased heat and pressure. So we can have igneous to metamorphic transformation, we can have sedimentary to metamorphic transformation, metamorphic to metamorphic transformation. All we need is heat and pressure. A couple of examples of this is stone, like slate and marble, things that people like to put in their kitchen. And then we also have anthracite, which is a type of coal. So that's a very popular metamorphic rock. All right, what I did here is I separated the types of rock into formation, types, and unique characteristics, kind of an easy study guide. If you want something a little simpler, I've also created this kind of bubble map about how rocks form. And so this is just about how rocks form. This is formation, types, and unique characteristics, depending upon how much you want to simplify everything. Last but certainly not least, we have weathering, erosion, and deposition. Weathering comes in two forms, physical and chemical. Physical is kind of the mechanical breakdown without changing the chemical composition or the elements. This is done by water, wind, or temperature, which happens when water gets inside cracks in rocks. It ends up freezing, so it expands, it breaks the rocks, and then when the water thaws, it kind of flows out and you're left with just a giant hole in your rock. Burrowing animals create physical weathering. Plant roots create physical weathering. And actually, fun fact is that physical weathering actually increases chemical weathering. So it kind of leaves the area much more open to being chemically weathered. And so chemical weathering is the breakdown by a chemical reaction. Primary minerals turn into secondary minerals. We'll talk about that a lot more when we talk about air pollution. Lichens are kind of special because they give off an acid that actually breaks down rock, and that's why they are a pioneer species in succession, especially primary succession, because they actually can release that acid that breaks down the rock and makes soil able to form, which is awesome. The chemical weathering depends on the rock composition. A lot of it nowadays especially is caused by acid precipitation or acid rain, which is a result of sulfur from fossil fuels interacting with the water in the atmosphere. If you don't remember that, you might want to check out the sulfur cycle in chapter 3. I made a little study guide for this one too. Weathering, I separated it into physical and chemical weathering, and then I talked about some environmental benefits, so why weathering is good, formation of soil precursors, reduction of atmospheric carbon dioxide, contribution of additional elements, especially things like phosphorus, which we don't have any in the air. It's all trapped in the rocks, and we have to get it out somehow so that we can survive. And then renewal of soil fertility. So, I mean, weathering isn't bad. It's not bad at all. Last sticky note today is going to be erosion and deposition. Erosion is the physical removal of rock fragments, so by wind, water, or ice. Erosion increases with slope, so the steeper something is, the more it's going to erode, especially if you remove all the trees. Burrowing animals also accomplish this. Deposition is the depositing of the eroded material, usually by wind or water. So if the wind picks up a bunch of sand from somewhere and then leaves it somewhere else, okay, or stops blowing, and now the sand isn't in its original place, it's in somewhere else, it has been deposited. Okay, kind of like you put money in your bank account. Now there are natural causes like streams, glaciers, wind, lots of erosion and deposition happening there. However, there are some human activities that cause this to be kind of accelerated, and that's deforestation, overgrazing, and construction. We're going to talk a lot more about these things in chapter 10 and 11, so stay tuned, and I will see you tomorrow.